Alrighty, we are going to talk about partial derivatives for two variable functions. Just a quick review here of derivatives. Going back to the very limit definition of if we have a single variable function, y equals f of x, then y prime, f prime, what, with the limit definition, are we talking about? Limit as h approaches 0, f of x plus h minus f of x over h. Right. Now, what does that mean? Because that'll help us interpret what it means with the partial derivative here. What does that mean? What are these things? If we've got a curve, whatever it is, y equals f of x, and we're trying to find that derivative there, what does this give us? Slope of the tangent line, okay. So slope of the tangent line. But even more yet then, this describes, well, it's the function value at a little bit past the x, right? So if we go out a little bit here to x plus h, then what we're finding there is how much this changes when x changes a little bit. Is another way to interpret it. So it's, yeah, it's the slope of the tangent line, but it's, if you change the function value just a little bit, how much does the function value actually change? If we change the input a little bit, how much does the function change, right? Okay. All right, so that's our derivative of a single variable function. Well, the problem comes then when we go to two variable functions, z equals the function of two variables. It gets a little more complicated, right? Because on a single variable, yeah, we're seeing how much the x changes, or if we change the x just a little bit, how much does the output, the y, change? Well, when we have two variables, we can change both of them a little bit. We can change the x a little bit, and so we can do x plus h. But we can also do the same thing for the y, and both of those are going to affect then the change in z, right? And so that's where it gets complicated, because you can change both of these a little bit, and that's going to change your output by whatever it does. All right, and so what we do is, instead of changing both of them at the same time, we're going to think about changing one of them and holding the other one fixed and see what happens there. And so hence the name partial derivative, because we're only going to do the derivative for one at a time, if you will. Okay? All right, and so, yeah, so we're going to define these partial derivatives. Here's the way we do that. We're going to define the partial derivative of f with respect to x, is how we'll denote it. The subscript, instead of using the, for whatever reason, instead of using the superscript, they use a subscript like that. Various reasons, I guess, but that's one notation for this. So this is the partial derivative of f with respect to x. And another notation is they'll use this, we use dy dx also, the Leibniz notation. Well, for partial derivatives, they'll use this symbol. I don't know, it looks like a backwards, somewhat like a backwards 6, I guess. But anyway, that's the partial derivative notation. And so this describes, again, the partial derivative of f with respect to x. And in terms of the limit definition, it's the limit as h approaches 0 of, our function's got two variables, but when we do the partial derivative of f with respect to x, we're just going to change the x a little bit and not the y. So it's going to be f of x plus hy minus f of xy divided by h. See what we did there? So basically, we're changing the x a little bit, but not the y. The y is staying fixed. Okay? All right. So that's the partial derivative of f with respect to x. Well, guess what we can do also? We can do the partial derivative of y with respect to partial derivative of f with respect to y, which you can also denote with that notation. And so that's going to be the limit as h approaches 0 of, well, we're going to change the y a little bit. So it'll be f of x y plus h minus f of xy divided by h. Okay? So the x is fixed here. Notice that. All right. Now, that's fine. That's what good. But let's talk about the geometric interpretation of this. Just like we did with the derivative of a single variable function. All right, so let's say we've got this curve out in space here, z equals f of y. And I'm going to draw it something like this. So it's kind of got a curve there to it. That's what maybe I should make this a little more curvy there. Okay. So we've got this rounded shape. Okay. Use your imagination there. All right. Now, what I'm going to do is, so this is our curve z equals f of xy. Let me talk about the partial derivative of f with respect to x for the point AB. And let's just say A, we're going to come out here, and then B, let's say is here. And so if we go up to the curve, then we're talking about, let's say, this point right here on the curve. What does this mean? Well, because of the nature of what we just talked about there, we're doing the partial derivative of f with respect to x, and so the y is fixed, right? Y is fixed. And so essentially, we're just dealing in the x and z plane, okay? And so one way you can think of it, if I slice the graph up here, the y is fixed, so I'm just looking at the yz plane here. And so essentially what I'm doing is I'm just looking at how this would look if I sliced it along the plane y equals b. right? Because that's our y value here. So if I slice the curve, since y is fixed, y equals b, that's fixed. So if I slice this curve, it's going to come out something like that, right? I mean, just a little hard to visualize, you know, 3D, some 3D graphics, I guess, would be in order here, but we're on a low budget, I guess. The low budget version here, okay? All right, so yeah, if I slice it, it's kind of like that. All right, now, so I'm looking at this point along this curve. And so what f of x, the partial derivative of f with respect to x describes then, it describes a tangent line, but it's tangent line to where that slice, that tangent plane slices the curve. All right, so the, call it C1, that's where our plane intersects the curve, so C1 is that curve. And so then we've got this tangent line to that curve, call it T1. So T1 is the tangent line to that curve, and it turns out the slope of that T1 is your partial derivative with respect to x, okay? So that's what it means, okay? All right, so what if we change it? What if we do, let me try to draw this curve here again, similarly as I can. Almost the same. Okay. All right. So if I go out to AV here, again, and then go up to the point that hits the curve there, or our surface, I guess I should say. What about f of y? Sorry, partial derivative of f with respect to y at AB? Well, on the partial derivative of y, of f with respect to y, mouthful, the x is fixed. X is fixed. I'm looking at slicing this surface with the plane x equals a. Okay, and so you just have to kind of visualize here. So if I go up at x equals a and slice that curve, well, it slices the curve differently than it slices it here, right? It's more in the x dimension there. All right, and so what would the partial derivative of f with respect to y then? So that intersects it at that curve. And so if I take the tangent line at that point to that curve, that is what the derivative describes then. It's the slope of that tangent line, T2. Okay? And so it does give you two different quantities, right? Because this one has this tangent slope, and then that one has that slope. So yeah, usually those values are going to be different numbers, different values. All right? Now, the good news on actually coming up with these partial derivatives is that our techniques and rules, product rule, quotient rule, chain rule, we don't have to go through that limit definition, you know, like we did when we first started doing derivatives. We don't have to do that because the same rules and techniques apply here. So let's go through a couple examples and see how this all works. All right, so let's say we've got f of xy equals x squared plus 3xy plus y minus 1. And we want to know the partial derivative of x, of f with respect to x, and the partial derivative, the other one, the partial derivative of f with respect to y. Okay, well again, the partial derivative of f with respect to x is going to, the way we'll work this is, since we're doing the partial derivative of f with respect to x, what about the y? Well, the y is fixed, and so hence, since y is fixed, in calculating this, we can just treat it as a constant, right? Because if something's fixed, it's not changing, so the rate of change is 0. So anyway, the y value, since we're doing this with respect to x, the y values, we're just going to treat it as a constant. And so here, that would be 2x, 3xy. Well, the y is just a constant, and so really, we're thinking that, right? 3y times x, just do the derivative of the x. That'd be 3y. That's a constant, so that's 0 derivative, 0 derivative. So there you go, 2x plus 3y. Then if we do the partial derivative with respect to y of this function, well, we're going to hold the x fixed, and so the x is going to be our constant in that case. And so the first term here, well, it's constant, so the derivative of that is 0. Here, we've got 3x times y, but that 3x is our constant, so just be 3x. The derivative of that would be 1, and the derivative of that would be 0. Okay? All right? And so that, then, if we wanted to get the actual values, partial derivative of x, I don't know. I guess we could do a 0, 0, 1. So if we wanted to do the partial derivative of x at 0, 1, which I think is on the, well, I guess we could do it anywhere if we want to. Let's do 1, 2. Yeah. So that, in that case, we would just do 2 times 1. That's 3 times 2. So that would be 8. Be the partial with respect to x. Partial at 1, 2 with respect to y would be 3 plus 1 would be 4. Yeah. Just have to plug the x into that one. Okay? So they have different slopes there, but it's, we're talking about different things. This one's with respect to x, this one's with respect to y. Okay. All right. Let's see, just to get a couple more here. All right, let's say our function is e to the x times the ln of x minus y squared. What's our partial there with respect to x? All right, well, both of these have x in them, so we're going to have to use our old friend product rule. We have to use a product rule here. So we're going to do first, that's the way I do it anyway, first times the derivative of the second. Well, we've got an ln. Remember back to our derivative rules for natural log. You do 1 over the argument there. But we're also going to have to throw in the chain rule, aren't we? The derivative of the inside. And it's just 1, though, okay? So we're lucky there because, yeah, this is the derivative of 0 since we're doing the partial with respect to x. So, yeah, it's just e to the x over x minus y squared. One way you could write it. All right, maybe a little more to it for partial with respect to y. One good thing about it, though, is that's just constant, so we don't have to do the product rule on this, right? It's just, that's just a constant, so it's going to stay the same. Yeah. Over here? Oh, I'm sorry. Thank you. I did forget. Let's go back to this one and finish it off. Yeah. Didn't finish my product rule, did I? All right. So back to this one. We've got, so that was the first times the root of the second. Now we've got to do the second times the root of the first, which is just e to the x. Yeah. All right. So, yeah. They might do something like that. Factor it off. Yep. Just checking, making sure you're keeping me straight there. All right. All right. Is that better? All right. The partial with respect to y should be a little easier, shouldn't it? Yeah, so this, if we do the respect to y, that's the only y in there, so this is a constant, so it just kind of comes along for the ride. Derivative of that would be 1 over, again, x minus y squared, but now, since I'm doing the derivative with respect to y, I've got to do that, negative 2y. And so how do we want to write that? Negative 2y e to the x over x minus y squared. I don't think that cleans up any. A little bit easier one. Less terms anyway. Do that one right? Yeah. Believe that one? Okay. All right.